This video accompanies Learning IoT with Python and Raspberry Pi. In this lesson, you will learn how to define functions that have parameters and define a function that returns more than one object. The example for illustrating how to define such functions is a program that predicts the performance of one or more cars. We'll write a program for car enthusiasts that predicts the performance of a car based on the time in seconds it takes the car to go from 0 to 60 miles an hour. In addition, the enthusiast should be prompted to enter an arbitrary time. The program should calculate the acceleration of the dream car in feet per second squared, the acceleration in g's, the distance traveled in the time to go from 0 to 60 miles per hour, the distance traveled in the arbitrary time, and the speed of the car at the end of the arbitrary time. Finally, the car enthusiast should be able to enter the times for as many cars as desired. This program will be composed of three functions: the calculate performance function, the print performance function, and the hot rod function. For brevity, we'll name the first two functions calcperf and printperf respectively. The hot rod function should prompt the enthusiast for the name of the dream car, the number of seconds it takes the car to accelerate from 0 to 60 miles per hour, and an arbitrary number of seconds. The hot rod function also calls the calcperf and printperf functions. The enthusiast should be able to get performance predictions for as many cars as desired. The hot rod function is defined to have no parameters, and it returns nothing meaningful. The printperf function should print out each of the calculated values with an explanation of what each value represents. The printperf function has 8 parameters and returns nothing meaningful. The calcperf function should calculate the acceleration in feet per second squared, the acceleration in g's, the distance traveled as the car goes from 0 to 60 miles per hour, the speed after an arbitrary time, and the distance traveled after an arbitrary time. The calcperf function has 2 parameters and returns 5 objects. We'll first explain the equations used to calculate these quantities and then describe the Python assignment statements. We'll assume that the car accelerates uniformly, and we'll also ignore forces such as friction and drag. Moreover, since we assume that the car is only moving in one direction, we'll refer to the speed of the car rather than its velocity. Assuming the car starts from rest, the acceleration of the car is equal to the speed of the car at the end of the acceleration period, which we assume is 60 miles per hour, divided by the time it takes the car to accelerate to that speed. In order to use this equation, all quantities must be in consistent units. And in order to convert the speed, 60 miles per hour, to units of feet per second, we multiply 60 by 5,280 feet, divided by 3,600, which results in 88 feet per second. Expressing the acceleration in g's makes it easier to grasp how the car is accelerating. 1g is the acceleration due to gravity at the surface of the Earth, and 1g is equal to 32.2 feet per second squared. To convert the acceleration from units of feet per second squared to g's, simply divide the acceleration by 32.2. The distance the car travels while accelerating from 0 to 60 miles per hour can be calculated by taking the product of the average speed and the time it takes the car's speed to increase from 0 to 60 miles per hour. Since the initial speed of the car is 0, the equation for calculating the distance traveled is the final speed of the car times the time divided by 2. The enthusiast is also prompted to enter an arbitrary time so that the speed of the car and the distance the car travels at the end of the arbitrary time interval can be calculated assuming the same acceleration. The speed of the car at the end of this arbitrary time can be calculated from the product of the acceleration and the time. This speed would then be in units of feet per second. An alternative equation will result in speed in units of miles per hour. In that case, multiply the ratio of the arbitrary time and the time to go from 0 to 60 by 60. The distance the car travels in this arbitrary time can be calculated by taking the product of the acceleration and time squared divided by 2. The distance will then be in feet. Note that there are other ways that these quantities could be calculated. On the next few pages are the Python assignment statements: the expression to calculate the acceleration of the car in feet per second squared, the expression to convert the acceleration to g's, the expression for calculating the distance the car travels while going from 0 to 60 miles per hour, an expression for calculating the speed of the car in miles per hour after accelerating an arbitrary time and starting from rest, and an expression for calculating the distance the car travels after accelerating an arbitrary time and starting from rest. The calcperf function has 2 parameters: the time for the car to go from 0 to 60 miles per hour and an arbitrary time. 88 is assigned to V60 because that is 60 miles per hour converted to units of feet per second. The acceleration is calculated first in units of feet per second squared, and then the acceleration is calculated to g's. The distance the car travels when it goes from 0 to 60 miles per hour is calculated, and the speed the car reaches after an arbitrary amount of time is calculated, and the distance the car travels after an arbitrary amount of time is calculated. The 5 calculated quantities are returned, and they're separated by commas. We'll save this into a file named Lesson Functions MO. Since the printPerf function prints out all of the values calculated, it should be passed values for the name of the dream car, the time to travel from 0 to 60 miles per hour, the arbitrary time, the acceleration in feet per second squared, the acceleration in g's, the distance traveled when it goes from 0 to 60 miles per hour, the speed of the car after an arbitrary amount of time, and the distance traveled after an arbitrary amount of time. Hence we define 8 parameters: dream car, T60, T, A, AG, X60, V, and X. We'll call the format method on the string literals in the print function calls. We'll format the time to 2 decimal places. We'll format the speed, distances traveled, and acceleration in feet per second squared to 1 decimal place, and we'll format the acceleration in g's to 3 decimal places. And this function will not return anything meaningful. The hot rod enthusiast will be prompted to enter the name of the car, as well as the time for the car to go from 0 to 60 miles per hour and the arbitrary time. The hot rod function is where the input function calls and the calls to calcperf and printperf belong. Since the hot rod enthusiast should have the opportunity to enter as many dream cars as desired, we'll use a sentinel-controlled while loop that ends if the enthusiast enters 0 in response to the prompt for the name of the car. We define 3 string-type objects. Time60 string, time string, and dream string represent the strings passed to the input functions. The string literals could be passed directly to the input functions, but using variables assigned at the beginning of the function instead makes the code easier to read. Since it is possible that the enthusiast might not enter a number for either of the 2 times, a try-except statement is used to handle the value error that might be raised. We place a try-except statement inside of the while statement so that the loop will continue to execute even if a value error is raised. In addition, we use an if-else statement to test if the enthusiast enters a 0 to 60 time that's greater than 0.01 seconds and an arbitrary time that is positive. Only if the enthusiast enters times in these ranges are calcperf and printperf called. Note that a time of 0.5 seconds for a car to go from 0 to 60 miles per hour is also unrealistic, but will allow such a calculation anyway. We'll assign the 5 quantities returned by CalcPerf to A, AG, X60, V, and X. We call printPerf with 8 arguments, the dream car, time to go from 0 to 60, the arbitrary time, as well as the 5 quantities just returned by CalcPerf. And we'll print out an appropriate message if the enthusiast fails to enter times in the proper range, and if the enthusiast fails to enter floating point numbers, we'll also print out an appropriate message. The final line in the while statement is dream car is equal to input. And we return, and the hot rod function is called. Now we'll test these 3 functions. First car is the Carnetti that goes from 0 to 60 miles per hour in 3.2 seconds, and the arbitrary time is 4 seconds. Next, try the hunk of junk as a dream car, which takes 35 seconds to go from 0 to 60 miles per hour, and the arbitrary time that we'll enter is 7 seconds. Third car is Dubla Pronto, but this time we'll enter an invalid time, a time that's too small, and hence we get unrealistic times. Try again. Try the Dubla Pronto, and this time in alphabetic characters instead of a floating point number, and we see invalid response. Try again. Third time of Dubla Pronto. And now we enter 2.9 seconds for the time to go from 0 to 60 miles per hour and 2.2 seconds for the arbitrary time, and we enter 0 to exit. To find links where the Learning IoT with Python and Raspberry Pi textbook is sold, go to learningiot.net.